Hello, I'm Dimitris Papoulias from IFIC Valencia, and in this seminar I will be discussing about our recent work on astroparticle physics with neutrinos and dark matter. I will start with the CEvNS, or coherent elastic neutrino nucleus scattering, which is this process shown by this Feynman diagram here, where you have a neutrino interacting with a nucleus. And coherent means that the nucleon coherent functions within the nucleus remain in phase, while elastic means that the nucleus, before and after scattering, remains in the same energy state. So this process um, is observed as long as the coherency limit is obeyed, and it takes place around energies from keV to a few MeV. So this process is a very interesting one because it has the largest cross-section in the neutrino world. For example, you can see here in this cross-section versus neutrino energy plot, the seventh cross-section is several orders larger compared to other processes. Like here below with dashed red is the neutrino electroscattering curve, and this one is the inverse beta decay curve, or these ones are neutron-induced neutrino processes. What is more interesting is that this seventh cross-section has a characteristic neutron number square dependence. So larger nuclei have larger cross-sections with a neutron number square scaling. And you can see here the various flux average cross-section measurements which have happened with reactor antineutrino experiments using a germanium target, with solar neutrinos using a xenon target, or with pion decay at rest neutrinos using argon, germanium, and also a cesium iodine target. So this was the good news. The bad news is that even though there are more events expected for larger nuclei, and you can see here for successively larger nuclei, the number of expected events is very much enhanced. On the other hand, due to kinematics, the available energy to be recorded by a given experiment, which is in this case is the recoil energy, is suppressed with a nuclear mass. So this was the main obstacle that made this process to be observed experimentally only after 40 years from the original prediction. So this first happened with the coherent experiment, which used pion decay at rest neutrinos at a spallation neutron source facility, and made the observation using a cesium iodine detector, a liquid argon detector, and a germanium detector. Then, the coming years, in 2022, Dresden-II experiment observed sevens with reactor antineutrinos, and early this year, the CONUS Plus experiment made its own observation using reactor antineutrinos and a germanium target. Moreover, at the end of last year, at the end of 2024, this process was observed also through solar neutrinos, solar boron-8 neutrinos, by two direct dark matter detection experiments, the PandaX-4T collaboration and the XENONnT collaboration. So in what follows, I will discuss our constraints on various beyond the standard model physics that we have obtained. And this happened through realistic simulations of the expected signals, taking into account all the ingredients. For example, we have taken into account detection efficiencies, resolution effects, or for the case of coherent experiment, we also took into account the energy and timing data, and we expressed the signal in a measurable quantity, which in this case is the photoelectrons. Or for the case of Dresden-II and CONUS Plus experiments, we express the signal in terms of the reconstructed electron equivalent signal, taking into account all the quenching factors and all these technicalities that I will not describe furthermore. We did so also for the case of the direct dark matter detection experiments, which observe sevens, the PandaX and XENONnT collaboration. In turn, they have expressed their signal in terms of electrons or observed electrons or observed photoelectrons. And worldwide, there are many experiments aiming to observe this process using stopped-pion beams or nuclear reactors. You can see many of them around the world here. And there are also many future or planned facilities aiming to do so. So let me start with the neutrino phenomenology using pion decay at rest neutrinos, reactor, and solar data. I will focus on nonstandard neutrino interactions as a characteristic example, and then I will also discuss our work on sterile neutrinos and production of new particles. Let me start with nonstandard interactions or NSIs. So these NSIs appear naturally in most neutrino mass generation models. These NSIs can be either charge current or neutral current. So you can see the two Lagrangians here. The charge current affect the production and detection of neutrinos, while the neutral current ones affect only the neutrino propagation in matter. So these operators are expected to arise generically from the exchange of some mediator, assumed to be heavier than the typical momentum transfer of the neutrino interaction. Our aim is to put constraints on these epsilon parameters, as you will see right now. So to begin with, let me show you first the phenomenological Lagrangian. For the case of standard model, the cross-section is shown as here. So you have a nuclear physics effects, particle physics effects, and kinematics. And in the case of NSI, so if we activate NSIs, this particle physics content will be updated to account for NSI. So the NSIs are accommodated by this parameterization of the weak NSI charts. So the first row contains the flavor preserving terms and the lower row contains the flavor changing terms. So these NSI couplings, like I said before, quantify the relative strength of the NSI in terms of the Fermi constant and can be either flavor preserving or flavor changing. So we have put constraints on both types of these parameters. By analyzing the coherent data, we actually performed a combined analysis of the cesium iodide and liquid argon data, and we superimposed the more recent analysis we performed for the case of CONUS plus data. So you can see here in various planes, flavor preserving ones or flavor changing ones, or combination of flavor changing and flavor preserving planes for both U and D quarks. You see our constraints put through the analysis of coherent and CONUS data, and you can see that both analyses provide complementary results. So what is more, the recent germanium measurement performed by the coherent experiment can help to break some degeneracies, or the even more recent dark matter direct detection observation of CEvNS from the XENONnT and PandaX experiments give access also to the tau coupling, which is not possible for the other two cases. Okay, another interesting process that we are working on is the so-called sterile dipole portal. So you can see you have an incoming neutrino interacting electromagnetically with a quark or with an electron, and in the final state it gives rise to a sterile neutrino, a massive sterile neutrino. So you can see that the cross-section is modified with these magenta terms to account for the mass terms of this massive sterile neutrino in the final state. So we did this kind of analysis using the coherent data, the PandaX-4T data, the XENONnT data, and also here the CONUS plus data. So in all cases, we perform a statistical analysis taking into account all the systematic effects, including also shape information or timing information whenever possible. And we have put these constraints in the parameter space of sterile neutrino mass versus the magnetic moment coupling for the different flavors of the magnetic moment, nu e, nu mu, and nu tau. So this nu tau is only accessible from the solar experiments, which are in practice direct dark matter detection experiments. So you don't see any coherent constraint in the new tau coupling case. And we perform also, our analyses are complementary to cosmological constraints or astrophysical observations from SN 1984 and also from Minibun, CHARM2, NOMAD, LSND, and various other probes. Another interesting process that we are working on is the production of an MEV scale sterile fermion through upscattering of nuclei or electrons that is mediated via novel mediators that you can see here. For example, here we present the vector case or the scalar case. So you have an incoming neutrino interacting through the vector or scalar mediator with a matter field and giving a sterile fermion in the final state. The two cross sections for these two mediator cases are shown here, with these extra terms to be the MK-dependent terms to account for the mass of the generated sterile fermion, while in this work we have done all the possible cases, including also the pseudoscalar axial or tensor interactions, but these are very suppressed. That's why I present only the scalar and vector ones. So we did the same uh, for the case also of LUX-ZEPLIN data and XENONnT data. And also we did the same assuming the expected data from neutrino electron scattering at the Dunier detector. And I present an example here. So all in all, you can see that in the mediator mass versus coupling plane, the direct dark matter detection experiments like LZ and XENONnT enable probing much smaller couplings thanks to their very low threshold capabilities, while on the contrary, Dune is not performing very well in the coupling plane, but it can probe larger masses for both mediator and the generated sterile fermion mass. This is thanks to the much more energetic neutrinos involved from the decaying flight at Dune. So these sterile fermions will not live forever, and they will eventually decay. So our initial idea was to see whether we are able to generate dark matter from the subscattering process, but we found out that these decays are rather fast, and so these decays can occur within the detector already. So we have two decay modes here, depending on the mass versus on the sterile fermion mass versus the mediator mass. And we took into account all these ingredients like the branching ratio, the decay rates, which are shown here, are summarized here, the detection efficiencies and everything. And we have put another set of constraints based on the decay of this sterile fermion to standard matter particles, an electron-positron pair in our case. You can see the various constraints for different ratios of sterile fermion mass versus mediator mass for the case of Dune and coherent. So let me skip subject now and focus more on dark matter direct detection phenomenology. And in particular, I will be discussing the neutrino fog and the case of boosted dark matter, which is a new inevitable dark matter component. So to put you in context, first, the typical constraints we are looking for is shown here. They are summarized here in this plot. So we have the mass, the WIMP mass versus WIMP cross-section plane. And you can see all the exclusion curves from the various dark matter direct detection experiments. And below you can see the neutrino floor. So neutrinos form an irreducible background source, and you can have neutrinos, astrophysical neutrinos from the sun, from the atmosphere, or diffuse supernova neutrinos, diffuse supernova neutrino backgrounds. Moreover, not only nuclear recoils, but also electron recoils can be induced from neutrino electron scattering. In this case, we take into account, of course, the efficiency, the reconstruction, but also we take into account the, the oscillation effects, because the standard model neutrino electron scattering cross-section is flavor dependent. In this case, we focus on the LUX-ZEPLIN and XENONnT data, and of course, this cross-section, the standard model cross-section, can be exchanged with a BSM1. So we have examples here with a neutrino melee charge, a neutrino magnetic moment, a neutrino charge radius, or some light mediator cases. So our purpose is to use this data to put constraints on various BSM scenarios. But before going there, let me also present another interesting plot. So you can see that depending on the nature of the interaction, if it is CEvNS based or neutrino electron scattering based, different solar neutrino components matter. For example, in the case of CEvNS, thanks to the kinematics of the process and the heavy nuclear mass, only the boron-8 neutrinos will leave a detectable signal given the current detection capabilities of the direct dark matter detection experiments, while for the case of neutrino electron scattering, mostly the PP and the beryllium-7 monochromatic neutrinos are important. So back to CEvNS rates, I present here a typical spectrum of differential events broken down by the various components of solar neutrinos, the diffuse supernova, which is here, and sorry, it is here, and the atmospheric neutrinos, which is here. What is interesting to notice is that assuming a 6-GeV WIMP with this cross-section, the signal of the WIMP can perfectly mimic the boron-8 one of the CEvNS case, or vice versa. And for the case of a 100 GeV WIMP and a much smaller cross-section, of course, the WIMP and neutrino-induced recoil spectra are perfectly matching. So this leads to a problem because beyond this level, you are not able to discriminate whether the signal is WIMP-induced or neutrino-induced. To do so, we have to tackle this problem statistically, and we did so in the past through the so-called neutrino floor that I discussed before. But a new definition of the neutrino floor, which is much more general, is the so-called neutrino fog. So in that case, the neutrino fog floor is not a hard wall like shown here, but because of the high statistics, you can discriminate and resolve even these small deviations of the 6-GeV WIMP, for example, versus the boron-8 CEvNS rates. And you can do the same for every neutrino component. So we will be using the neutrino fog from now on, which is more generic. And so we have an ongoing work on this neutrino fog setup, and we want to explore the implications of new interactions through light mediators in the neutrino sector or dark matter sector. So we did so, and we analyzed the recent data from XENONnT and PandaX-4T experiment, and we have put constraints in the coupling versus mass for the various mediator masses planes, and we see that the case of dark matter, of mediators in the dark matter sector, generate much more stringent constraints. So we're interested to see whether these constraints, have any impact on the neutrino fog, and indeed they do. So we have chosen these parameters and for the scalar and the vector case, which respect the limits shown here on the left-hand side of your screen. And we have seen that the presence of the new physics or through the new mediators in the dark matter sector gives rise to an enhancement of the neutrino fog for the low energy components of the solar neutrinos. So we find this very important and very interesting because in a future in a future experiment with further low energy, low threshold energy capabilities, this will become a serious concern. Another idea beyond the typical thermal relic dark matter is the following. So, of course, the relic dark matter will just come in the Earth and interact with the detector, but it is a non-relativistic scattering. In the case of boosted dark matter that I will be discussing here, we have the following setup. So we have the dark matter in the universe before reaching the detector, but these dark matter particles may have interacted already with, for example, the diffuse supernova neutrino background. And after this interaction, these dark matter particles have been accelerated to relativistic velocities. So, a relativistic dark matter is important to notice that opens the low mass region beyond thermal relic limits. So, first of all, this is an inevitable component of dark matter, the boosted dark matter, but also it enables probing dark matter masses below the typical threshold of given the current detection capabilities given the various thresholds of the dark matter direct detection experiments. So, and we didn't stop only there, but we also took into account Earth stopping effects, which lead to an attenuation of the dark matter flux. So, for example, imagine that the dark matter particles strikes the Earth from this point. So this is the entry point, and here is at Grand Sasso, the XENONnT experiment is the outgoing point. But the dark matter along this path through the Earth, within the interior of the Earth, will have interacted with various particles of the Earth. This will lead eventually to an attenuation of the flux that reaches the detector. So we have analyzed this impact, and assuming boosted dark matter, we are able to use the data of XENONnT and LUX-ZEPLIN experiments in order to put constraints on the parameter space of dark matter mass versus cross-section. And we did so assuming interactions with electrons or interactions with nuclei. In the former case, we find that all the region that we probe is first of all excluded, but of course it is complementary to existing constraints from, for example, solar refraction or the super Kamiokande. And you can see that the constraints extend beyond the reach of the direct dark matter detection experiments, assuming the standard relic dark matter. For the case of interactions with nuclei, on the other hand, you can see that we put new constraints complementary to cosmological ones and extending, of course, beyond the direct dark matter detection experiments, and also complementary to constraints from BBN. So now, in the final part of my talk, I would like to focus on our recent work in which we are interested to open new directions in neutrino experiments. So our aim is to utilize current facilities, mainly looking for neutrino interactions, to probe different particles. For example, like I will discuss in a moment, axion-like particles can be probed in a reactor neutrino facility, and sub-GeV dark matter can be produced in a stopped-pion facility. Let me start with the former. So, at a reactor antineutrino experiment, the reactor power plant not only produces an abundant flux of antineutrinos, but it also produces an abundant flux of photons. So these photons can be produced because of fission or decay of fission products, capture processes in the fuel, an elastic scattering or decay of captured products. And it is quite abundant, as you can see from this flux versus energy plot. So these photons, after they are produced, they interact already and directly within the core of the fuel. So they interact with uranium, basically. They interact through various diagrams here. So there is Rayleigh scattering, Compton, photoelectric absorption, and electron pair production. You can see the various components here along with their strength. But what is important to notice here is that a fraction of these photons, which are very abundant, like I said, can be converted to ALPS. So we will take this into account and assume a phenomenological parameterization via dimension 5 effective operators, which enables us to write these couplings between photons and ALPS, between electrons and ALPS, or between nucleons and ALPS. So the first two will lead to a continuous ALP flux, while this one, that I will not discuss further, will lead to monochromatic ALPS because of nuclear de-excitation. Of course, this interaction will proceed through a Primakov channel for the case of ALP photon couplings, or through a Compton-like channel for the case of ALP electron couplings. So these ALPs, after they are produced at the reactor core, they traveled all the way to reach the detector, which in principle is a neutrino detector, but they can interact with the target material of these detectors through the inverse processes. So through the inverse Primakov and inverse Compton channel. I have here the cross-section for the case of Primakov scattering. The inverse Primakov scattering channel has the same cross-section up to a factor 2 to account for the different spin orientation of the initial and final states. And also we have furthermore considered the decays. For the case of the ALP photon coupling, we have the diphoton decay that you can see here. So we have analyzed the expected data of these ALP signatures and compared them with the expected data of neutrino signatures at the same experiments. And we have put constraints in the parameter space of ALP photon coupling versus ALP mass, or combinations of ALP photon coupling times ALP nucleon coupling versus the ALP mass. You can see that our constraints for reasonable assumptions of the future detectors and reasonable backgrounds are able to probe solar experiments like CAST and SUMICO, or observations from HB stars, or astrophysical observations from the ALP effects in neutrino emission using the CEN 1987 data, and also to probe the beam dump constraints. What is important to notice is that, for example, this proposed experiment will take place under controlled laboratory conditions. And for example, these solar constraints may not apply at all if in-medium effects occur. And also, you can see here this white triangular area, which is very small and still unconstrained, can be constrained by our proposed experiments. And so this is called the cosmological triangle, with which you can test the assumptions of the lambda CDM hypothesis. For the case of the other plot from the combination of ALP photon coupling and ALP nucleon coupling versus mass of the ALP, you can see that our proposed experiment is able to probe again the same regions of CEN 1987, of HB stars, of Borexino, Texono, and also extend further the constraints to constrain more this parameter space. The final setup that I will be discussing is the case of artificially produced sub-GeV dark matter at the spallation neutron source. So the situation is as follows. So you have the spallation beam, which is protons, hitting a target, and in principle it gives pions, which in turn these pions generate neutrinos and other particles. However, if this diagram exists, the pion can not only decay to a diphoton pair, but it can decay to a photon and a dark photon. And the dark photon, in turn, it will decay to two dark matter particles. Here we assume the case of scalar dark matter, not fermionic dark matter, because the latter is constrained by the CMB, is excluded by the CMB. So these dark matter particles, eventually they will reach the detector and interact through this diagram with a nuclear target. So we have performed XENONNT-4 simulations of the spallation source, assuming all the ingredients, the operation power, the detector dimensions, and everything. And we are able to reconstruct the expected dark fermion, dark matter flux in the energy and angular space. And we assume two examples, the two facilities, the J Park in Japan and the European spallation source. So we have analyzed the expected signals and compared them with the expected standard model signals from coherent elastic neutrino, neutrino nucleus scattering. And we have put constraints in the parameter space of the dark photon mass versus this complicated parameter here, which contains the dark matter mass, the dark photon mass, the epsilon and AD couplings. So you can see that with our setup, both the ESS and J Park, if placed at 30 degrees of axis, where we have the maximum of the angular flux, they will lead to improved constraints compared to current measurements by the coherent experiment or the coherent Captain Mills or NA64. And also, they will extend beyond the relic density curve that you can see here. So with that, I will close this seminar. I didn't go through any details of or equations as much as I could, but please feel free to reach out in case you are interested for more details from me. And again, thank you very much for your attention.